How's it going? Hanging in there? So, are there any questions administratively about what's going on in the class? Any questions? There have been emails about the exam, and Proj is working to resolve them, and I think we're going to be able to accommodate most of the requests. Okay. Again, the exam is a week from today. Many of you will be on College Ave, and in fact, if there's anyone that lives on College Ave that would rather take the exam on College Ave, please let us know soon, okay? Because that was not necessarily a question. You know, you might be content to come here, but if you would actually prefer to take it on College Ave, that'd be great, okay? And it would help out other people as well, given the initial assignment of locations. And again, you can bring one sheet of notes, front and back, handwritten. I think the instructions hopefully are pretty clear. There's an announcement, and my plan is to copy and paste the instructions that you see in that announcement on the top of the exam, okay? You'll be given enough pieces of paper to write on, and you will not be writing on the questions themselves, so please don't write on the questions. Write on the answer sheets that you're given. Any questions on that? All right. Today is the last topic that will be covered, I guess you could say, or eligible for inclusion on the exam. And you won't be doing finite element analysis. Oops, what was this? Oh, okay, that's interesting. All right, you won't be doing finite element analysis, but you will be responsible for understanding thermal stress and thermal strain. Okay, and so we'll introduce and we'll spend quite a bit of time on these topics today. So, how many of you have used some type of simulation software for calculating displacements or calculating stresses in a structure? Yes. Okay, so what did you use? Okay, go ahead. SolidWorks? Okay, great. SolidWorks, great. What were you working on?
I think it was like a propane tank, just like pressure and displacement.
Okay, that's great. If you're using a propane tank, those sound like they could be somewhat thin walls. So you had kind of large dimensions in this direction and this direction, right? Large radius, large height. So were you using shells as your elements, or were you using like just? Okay. Okay. All right. Okay. What else? What were you working on?
I was working on rocket engine testing.
Rocket engine testing. Okay. So again, you have a kind of circular structure. Did you use an axisymmetric model, or did you?
I was working on the actual stand itself. So
Okay.
Pretty much the way it worked is I was putting whatever force I wanted rated for. I think it was 150-pound force, and just applied the 150-pound force directly downwards where the rocket engine fires.
Okay. So you're working on a test stand, and you had it was not axisymmetric. You had like different trusses and things coming out. It was 3D in nature. Okay, great. There were some other people. Who else has done some finite element analysis? Anyone else? Okay, so today we're going to introduce it. Now, if you've used other software, I'm going to ask you to not use that software, okay? We're going to use the software that everyone will have access to in the class. Hey guys, up in this region, it'd be great if you could just keep the conversations like 20 decibels lower. Okay, so today we're going to use FreeCAD, and we're going to use something called PrePoMax. Both of these are open source solutions. Okay, FreeCAD. Has anyone used FreeCAD before? Yeah, and then you ran away from it probably. Yeah. All right. Don't worry, we're not doing very complicated geometries today. So FreeCAD is going to be what we use to create a very basic bar that we can test. Okay. We need to get it into a 3D format, and this is just an easy way to do it. If you want to do it with SolidWorks, that part I'm fine with you doing in SolidWorks. But the actual finite element analysis, we're going to use this other software called PrePoMax. And that is based off of the actual solvers are using, or the solver that's being used is something called Calculix, which is also open source. Okay? You have a variety of packages available for both creating geometries and doing what we could call computer-aided engineering, or finite element, or finite volume, or a whole host of other different types of numerical simulations. When you take multi-physics simulations, your junior or your senior year, you will use ANSYS, right? So has anyone used ANSYS before? Okay, you were using ANSYS? Great. Okay. Has anyone used COMSOL before? Okay. So these are kind of the two big commercial packages that are available in the realm of multi-physics simulations. And anyway, we use, if you learn how to use ANSYS, you'll be able to use COMSOL. I like what Professor Singer has kind of said about these two. Well, I guess, I don't know, I guess we shouldn't have any biases, but COMSOL is kind of like the Cadillac, and ANSYS is kind of like, I don't know, a whole bunch of cars that are hard to use, okay, or drive, okay. But once you learn ANSYS, you'll be like, oh, all right, if I get an opportunity to use COMSOL, I will. But the industry standard has more leaned toward ANSYS, actually. That's feedback we got from our industrial advisory board, so we're going with ANSYS. Okay? But academics, we love COMSOL. And there are a host of YouTube videos out there to be able to do kind of basic simulations to get you started. And both ANSYS and COMSOL have extensive support on their websites. So we're going to take a very basic problem that we've been analyzing, and we're going to implement this in PrePoMax. We're going to do finite element analysis. Okay, and we need to kind of do two things. We need to, and that's why. Well, PrePoMax, it stands for pre-processing, post-processing to the max, I guess. I don't know what they were thinking, all right? But that's not a bad way to look at these types of problems where you're running numerical simulations. You have to create the geometry, you have to prepare it, and then you run the analysis, and then you kind of post-process your results. A lot of organizations, so SolidWorks and these other companies, they've recognized that there's an opportunity to bridge the gap. Even so, when I spent some summers at NASA, you had kind of your design group and you had your analysis group. Okay, and so the design group would, use back of the envelope calculations. They use their experience, use their ability to create. It's a really important skill, right? And then they would get their drawings done, and they might have, I don't know if they were using SolidWorks, Pro Engineer, whatever they were using, can't remember. And they throw it over to the analysis people. Analysis people then bring in all their CAD files, and they're using things like CATIA, CATIA. All right, and they're doing the analysis. They've got the skills, and then they throw it back over to design engineers and say, "Look, you got to beef it up in this region. This is where it's going to fail." You know, and so SolidWorks and some of these other companies, they're realizing that if you have at least an initial ability to do this analysis before you like send it over to the specialized group, you're going to potentially save time. Okay, maybe even take away people's jobs. Who knows? But you're going to so you got to kind of be able to work in both of these domains. Garbage in, garbage out. Okay, so what I'm going to show you today is hopefully not too much garbage, but you'll begin to see that you need to have some experience, you need to have some understanding of what we're doing in mechanics and materials to interpret these results, okay? And just because the stresses that you calculate are lower than the yield strength of the material, that does not mean that you're home free, okay? As you go further, you'll realize, oh yeah, there's all kinds of stuff that can happen that makes this complicated. What's happening in the sharp corners? Okay, what's happening if this is a cyclic load instead of a static load? A lot of different issues. Okay, but what we're going to start with today is a bar. It has a length of 5 centimeters, and then it has a cross section that has 1 centimeter by 1 centimeter. So it has a cross-sectional area of 0.0001 meters squared. And then we have a force, an axial force that's being applied, and the material has an elastic modulus of 200 gigapascals and a Poisson's ratio of 0.3. Okay, and the question is, what are the normal strains in the bar? Okay, and you know, we can also figure things out like what is the normal stress in the bar too. Okay, so let's get started. First, we're gonna create the geometry in FreeCAD. So FreeCAD you can get from their website, okay, and you download it. And this will work on a Mac or on a PC. All right, so you know, you just click download now. I installed it this morning, so I have, I think, 0.2.1 on my computer. I had 0.2. I don't know. I had maybe 0.2.2. I'm not sure what it is now, but I'm just going to go ahead and get it started. Okay, and this will run on a Mac or a PC. All right, and at least FreeCAD, I was able to get it to run. You know, we have the Rutgers virtual labs. I don't know if you've used it, but I was able to install FreeCAD and run it on the Rutgers virtual labs. Okay, and that was fun. That was nice. Okay, I had trouble with PrepoMax. PrepoMax would run on the virtual lab, but it crashed on me. Okay, so you might need to find someone else with a PC, or you might need to run it in the labs here in EIT or DSV. Okay, if you don't have a PC already. So this will come up, something like this, and we're going to go ahead and we're going to click the Create New. And I, like down here, the one thing that may be a little bit different, I think it uses like maybe this CAD or something. I don't know. I just have the Tinkercad setting for my mouse. So, you know, you might want to have a mouse for this. We're going to go ahead and we got the part coming in. We have these different kind of workbenches, you could call them. You can do part design and that would be okay. But for this particular problem, part is actually probably simpler. And then we come over here and we select a cube, and it brings in a cube. We click on the cube, and we just give it its dimensions. All right, so it's going to be 50 millimeters long, and then it's going to be 1 centimeter by 1 centimeter. Okay, so we got 10 millimeter by 10 millimeter. So we're done. All right, that's all you have to do in this part, except export. All right, so we're going to export this. Okay, yeah, I'm sorry. You had to select that object. Now we hit export. And we're going to use an STL. So, you know, you're going to go through here. I think it knows that I like STL. When I installed it this morning, it was kind of like, hey, which one do you want to use? Just use STL. And fine, I'll overwrite what I called a normal bar. Okay. So, yeah, sure, we can replace it. So now we've got this piece of software, or this model done. The next thing we're going to use is something called prepo max. So you can just type in prepo max into Google or DuckDuckGo, and you come here, and we wait. All right, and we can go to downloads, and so I've used older versions. This morning I was like, let's live on the edge. All right, so we're trying out their development version. All right, and I thought maybe the reason it wasn't working in the Rutgers Virtual Lab was because I was using the development version. So then I went back down to one of the more stable versions, and it also crashed on me. Okay, so I don't know exactly what's going on with the virtual lab. All right, so but keep that in mind. So I'll go ahead and we'll try the bleeding edge again and see if I can remember how to do this. The user interface was a little bit different. What's kind of unique and fun here is that you're going to save, and so I understand we live in 2024, so people are not as familiar with file systems. At least that's been my experience working with you younger generation who know how to use things like TikTok and Instagram and stuff that I don't know how to use. But back in the day, there was something called DOS, okay? And DOS was all about files and directories. We didn't call them folders, we called them directories. Anyway, so here, I'm just going to download this one to my downloads directory or file folder, okay? And it's it's a little bit large. It's 160 megabytes or so. Okay, so it's still going. Wow, I must be using a lot of bandwidth in here because this is 2024 and it is boggy. All right. Well, let's go over and come into the downloads folder. All right. So this is what's downloading, I guess. Okay, now so it's one of these. Okay, I guess this is the one we just downloaded, 1227. So, okay, you right click and then you extract all, and we can extract it right there. Okay, and my computer, all right, that should be independent of the internet, but it's of course doing a bunch of processing, and it's not the most powerful machine. Okay, and maybe I'll go ahead and I'll close FreeCAD because I don't need this anymore. So give my computer a little bit of I can discard it. I've already saved it as the STL, and so I don't need to keep that file. All right, and so now this is a little bit different. This is not your standard. Like the other thing that impressed me recently was I was doing something with the first year students, and they're like, "Oh, this is an app on a PC." I'm like, "App? Who calls this stuff app?" But I guess that's what we call them now. It's a program, all right? It's a piece of software, and we go into it, all right? And this is gonna upset people, all right? But what you see is we're not installing anything. We're running an executable directly. You see that? We didn't install. We are running the executable. So you just double click on prepomax.exe. And if this is, okay, I'm just making sure I don't have too many things going. Maybe I do, I probably do. Maybe I didn't double click. Maybe that's my lack of understanding. But we're gonna open this. Okay, I guess I didn't double click. Okay, it's gonna send a scary message. You click more info and we're gonna run anyway. All right. Okay, and then it comes up. So once you've got it up, we're going to create a new model. It's going to be a 3D model, and let's just use meters, kilograms, second, and degrees Celsius. Okay, we hit OK. Then we are going to import our bar, all right, our STL file, and we do that. Now, here's the bar. All right, isn't it beautiful? Does anything strike you as odd about this? Are there any issues? Just look at the image. Yes. Okay, it's not connected to a wall. Okay, yeah, okay, it's not connected to a wall. That's a good point. All right, it's in space. Anything though, be a little bit observant. Yes, Mark. The length. What did we say the length was? We said it was 5 centimeters. Look at the scale bar under there. 36 meters. Okay? And in fact, if I bring it down a little bit, if I can, maybe I can't because I'm not as. Oh, there we go. All right. See, like I can zoom in a little bit, or I can zoom out a little bit. What does it look like its length actually is? 50 meters, right? That's not what we want to solve. So this is a common problem whenever you deal with STL files and you go from one piece of software to another piece of software, okay? If you do it with SolidWorks, you're going to probably have similar issues. I don't know what the scaling factor is, okay? So what we do is we come over here to geometry, we go to the part, and we go to transform, and we go to scale. And we're going to scale this by 1/1000 in all 3 dimensions, okay? And we hit apply, and poof, it's gone, all right? Don't hit apply again. It's like, you know, we can just keep shrinking it, all right? Okay, so we close that, and of course, this software, well, maybe not of course, the software is awesome for what it is, but nowhere close to a commercial product. All right, so you click on this thing that says zoom to fit, and voila. All right, now we've got it, and it looks like it's about right. Okay, so now we can come over here, and this is an object. It's like the table. What does finite element really mean? It means that and so this, you know, theoretically has infinite number of material elements, right? Of infinitely small size. Finite element means we are going to discretize this object into a finite number of objects that are interacting with each other, and we're going to see what the result is. So we come over here, and we're going to use the mesh. We're going to create a mesh, and we're going to click on mesh parameters. We're going to click on part. We're going to click on this, and that's where it crashed. So if it crashes for you, I don't know what to do. All right, find another computer, maybe change your settings. You know, I couldn't run as an administrator on the Rutgers Virtual Lab, so that might have, I don't know. Find a compatibility mode. I don't know what to tell you. All right, but that's where it crashed. Okay, and then here you get to play with this number a little bit. Okay, this is saying, okay, what's the minimum element size and what's the maximum element size, and you will get a feel for this as you do more simulations. If you had if you know, you could have a finite element model where it's just like 3 blocks inside. Okay, given our computational power, that's not the most effective, okay, number of elements to kind of get the behavior we want. So you can kind of play with this. If I put it down to 1.5 millimeters for the maximum element size, in this case, I hit OK, and then I do create. Whoops, these are just the parameters. Sorry. Now I go to mesh. Sorry, and I create the mesh, and it takes a second. That doesn't look bad. You see, there these. You know, we can only see what's really on the surfaces in this case. All right, but you see, like, it looks like you've got a lot of elements, right? Enough that, you know, maybe there's, you know, well, it tells us there are 6,795 elements, and there are 11,268 nodes. Okay, because it has, even though it's not showing all of them, it has discretized the entire volume. Okay, so what do we do now? Well, we're going to, I guess, there's a tree here, and we can kind of attack this in different ways. Maybe I'll go from top to bottom, but it won't necessarily be clear why we're doing things why we're doing it. Okay, but what we're going to do, we are going to create a surface on this side. This surface is going to be where we apply the axial force. Okay, and that axial force is going to be distributed over that entire surface, and that's what's going to be pulling the bar axially. All right, so we'll go ahead and we're going to create a surface, and we'll do selection, and we'll do right like this. Boom. Okay, surface 1 created. Okay, we're actually also going to create a reference point. This reference point is where we're going to apply the load. Okay, So we're going to create it, and the easiest thing to do here is actually specify the coordinate. This was 5 centimeters long. So, and you see we have a coordinate system x, y, z, so it's in the x direction. So we're going to say 0.05, okay? And look, it moved it, but look, it moved it to a corner, right? So that's because it's, y is 0 and z is 0. So at least PrePomax and FreeCAD are communicating about, okay, where the origin is. Sometimes when you use other pieces of software, they don't even agree on what the origin is, okay? And then that makes things kind of messy. All right, so we're gonna move it up to the middle, all right, up to here. So we're gonna go up 2.5. Oops, yeah, I think that's right. No, oh no, it's not 2. It's a 1 centimeter by 1 centimeter, so it's not 2.5 millimeters. It's 5 millimeters. That will get us to the center. Okay, you see that? So that's where the reference point is, and we hit OK. So that's where the force will be applied. Okay. Coming down. All right, so materials. Let's go ahead and create a material that has elastic properties. So we can grab here and drag over. Oh, no, maybe not. Maybe I better use this. Okay, use that. All right. And the elastic modulus we were given in this problem. Whoops. Not there. Where are you? Okay, elastic modulus is 200 gigapascals, and the Poisson's ratio is 0.3. All right, so what material is it probably? Steel, probably steel, okay? So we can do 200 GPa, and we can do 0.3, just like that, okay? And that's what we want there. Okay, sections. We need to create a section. We're going to create a section, a solid section for the entire part. Okay, so we just click on it, boom. All right, and it's done. So that's a section. In terms of a constraint, we're going to create a rigid body. Okay, this is going to link. You see that's reference point 1 to a surface. And what's our surface? Surface 1. That's the only one we created. So they're linked. That means that when I apply the force to that point, it has this surface that's a rigid object. What does rigid mean? It means that it's not going to bend. Okay, so when I apply it at that point, it's now distributing that force over that entire rigid surface that does not bend, but is attached to the rest of the body. Okay, so that's kind of a nice way to connect them and be able to get a contact force then distributing over a larger area. I don't think we need, we're not going to use any contacts here, all right? And we need to add physics, all right? So in other packages, they'll be like physics. What kind of physics do you want to use? All right, and that in this software is called steps. So these are the analytical steps. So we're going to create, and what we're going to do is add a static step. We're just doing statics, right? That's what this class is about. We will actually, if we have time, I'll show you how to do some thermal stuff too. But we hit OK there. Okay, now, finally, who was it? There was no wall. Who said there's no wall? All right, we got to add a wall. Okay, so we come over here to boundary conditions. We're going to create a fixed wall. All right, just like that. We hit OK. Okay. That doesn't necessarily look like a wall, but it is a wall, okay? And we need to add a normal force. So we come over here to load, and we're going to create a concentrated force, and we're going to use it at the reference point, okay, just like that. And here you're going to see F1, F2, F3. And in PrePomax and other softwares, sometimes instead of saying X, Y, Z all the time, they do 1, 2, 3. All right. So obviously 1 goes with X, 2 goes with Y, 3 goes with Z. At least usually. I've had issues with the coordinate systems in PrePomax in the past. I hope at least for this problem it's not going to be a problem, or at least for this today we shouldn't have any issues. But when we start doing things with shear and shafts and beams, I have had some issues with it. I don't know, and we'll see once we get there if those things have been resolved. Okay, so we're going to apply a force of 1,000 newtons. That was what the problem said, in the x direction. Okay, and it's got a magnitude here, and we hit OK, and wow, all right, great, it's coming out. 1,000 Newton force right there. Okay, and if I have not made any mistakes, I think we're ready to go. Okay, so we're going to go ahead and run the analysis. It takes a little bit of time, but it's actually probably faster than you or I could do that analysis. Well, definitely faster than the finite element. Okay, but whether this is more, how do you say it, more efficient than doing the hand calculations, that is debatable. All right, so now, oh, what happened? Oh, I think I need it. Let me just run it again, or maybe results. Yeah, if I click on results, there it goes. Okay, so here are the results. All right, so what are we looking at here? What in the world are we looking at? Okay, this tells you over here. So this is where color is nice. All right, it tells you what it's showing in its colors. So this is DISP. What do you think DISP stands for? Displacement, right? It doesn't stand for 4K display or something like that, right? It's your displacement. And it even tells you what the units are, right? That's meters. So this is going to be giving you the displacement all three directions. Okay? Now, what if, and it says, because this is all, right? What if I only want displacement in the x direction, right? And that's kind of where we typically are for this class. I can select that. So that would be U1 here. That's displacement 1, and it's in meters. And this node right here is telling us where the maximum is. Theoretically, this is at the same spot as that, right? Or it's, when we were talking about averages, right? Theoretically, this spot is at the same spot as all of these, right? But this is a numerical solution, okay? And it has a lot of decimal points at the end. So it's going to show us things that we don't necessarily, that are just nonsensical in a sense, right? Like the fact, for example, here that the max is at this node. Is it really any different than, say, here or here or here or here? For our practical purposes, probably not, okay? The other thing you can do is you can right-click here and you can do a query. And you can select. So let's say we want to select right there, right in the middle, because I'm a little more comfortable with trusting that, okay? So now it tells me that, again, it's like exactly the same number, at least to those three decimal places or 4 significant figures, right? And that's the result that I've got. Okay, so I can hit close, and now that's there. What if we want to know stress, right? Which of these stresses, you see this is called stress, right? Which of these do you think is of most interest to us? Anyone? Anyone? Huh? Okay, S12. Why do you say S12? Well, I mean, I have no problem clicking on it. Huh? Okay. Yeah. So, S12. This is interesting. All right. And there is a value there. Okay. You can see that there are some stresses. Okay. S12 though, that would say, okay, we're interested in the x face in the 2 direction, right? Because just think of those as those are the subscripts. S is the sigma 1, 2, so that'd be like a sigma xy, right? And we know we don't really usually write a sigma xy. We actually write tau, right? So that'd be like a tau. That's a shear stress. In this case, we're not so interested in the shear stress. It does exist. That's fine, okay? And if we look at it, it's down at like, 10 to the 4th. Okay, pascals, at least in our area, okay? And I can put another query over here on the side. But look at this. At this location, it's only 13 pascals. Okay, so interesting stuff is happening at the edges. Okay, notice that. Why is that happening? Why do you think there's So this is kind of like saying, okay, I thought the stress would be low, the shear stress would be low, right? Because this is not a shear stress problem. This is a normal axially loaded one. But why do you think there are, kind of significant shear stresses? Like it even says 10 to the 6. Why are there shear stresses at these boundaries? Just think about what is shear stress. Huh? Okay, yeah. So like you're thinking, all right, it's if this is sigma 1 2, if it's tau 1 2, it's tau x y. Okay, which direction is the x direction? Well, the x is on. So this would be acting on this face, right? That's on that face, and then it's acting vertically. Okay, that's the direction of the force is. And so why at those boundary conditions do we have this behavior? Yes, Michael?
It's because that like the way it's deforming, it's using one construction.
Yeah, okay, so it has to do with deformation. And remember, we said those constraints are fixed in terms of, well, okay, let's put it more clearly. This side is fixed. So it's not letting those nodes move in X, Y, or Z. All right? This is allowing there to be displacement in the X, but it's not allowing motion in Y and Z. Okay? So does this material, like if I'm just pulling it out, what do I know if it's a real material? With a Poisson's ratio, we know that material is going to want to contract, right? As I pull this direction, it wants to contract. But I'm telling it, no, you're stuck at these locations, right? So there are shear stresses involved in essentially maintaining equilibrium that says, oh, you really want to move, but I'm not going to let you. So that's why when you look at these boundary conditions, it's very important that we have an idea of what is happening and what's real and what's not real. So going back, the one that I think now at this point people are like, yeah, what I really am interested in is sigma x, right? Because that's the axial stress. So S11 would give me, right? Remember we said we don't normally write sigma x, we just write sigma x. We don't normally write sigma 1, 1, all right? So this is the axial stress, but once again, we do see that there's some strange stuff happening at these edges where those constraints have been added. So if I'm interested in really understanding what the normal stress is here, I go away, like for our intents and purposes in this class, I don't do my analysis on these boundary conditions because they're scary. Okay, I don't know exactly what's happening. I go to some place like the middle. And you see that? This tells us S11 is, what is that? 1E7 pascals. What is that? Yeah. 10 megapascals. What was our force? It was 1,000 newtons. Okay. What was our cross-sectional area? Well, it was 1 centimeter by 1 centimeter, right? What's that in meters squared? Yeah, it's 10 to the negative 4, right? Meters squared. So I've got 10 to the 3 newtons over 10 to the minus 4 meters squared. That gives me 10 to the 7 pascals. So we're right on, right? See, this is where you want to, so when you're doing a project, the first thing you want to do is you want to put your really complicated geometry into the finite element software. And then you have no idea if it's garbage or goodness, okay? What you got to do is do some simple cases where you're like, oh yeah, that's my analytical calculation. I can trust now that at least I've got a process where the stresses that I'm measuring match the stresses that I just calculated by pen and paper, or pencil and paper, or Python and whatever, okay? Or Google, right? You got to do these, I call them baby steps. If you take multi-physics with me, I'd be like, baby steps. do the baby step first before you jump into the teenager, okay? Because the teenager is super complex, super complex. All right, there's all kinds of stuff going on there. All right, so that is a good baby step. All right, now what did we say? Remember, we did a hand calc, or I did the hand calc, I guess, for the strain in the x direction. So look at this, right? This is pretty simple. I have epsilon x, right, is equal to 1 over e times this large equation. I do have a Poisson ratio. Do I have any sigma y and sigma z? Well, I might next to the boundaries, right? But in the middle region, no, right? It should be like whoop, zeros, okay? And then it's just the sigma x over the elastic modulus, which I plugged in, and so we should get 50 microstrain. That's what we should get, okay? In the x direction. So let's do a couple of things. First, let's look at S22. Yay, S22 is not 0, but it's 130 pascals. That's a whole lot less than 10 to the 7th, right? And again, this is where you want to do your checking. Like, does this make sense, okay? If I do sigma z, right, again, oh, it's even smaller. It's minus 2 pascals, right? That's, that's good enough for our intents and purposes. Okay, so that's stress. Now let's look at strain. Okay, here's the moment. Epsilon x. Boom. 5e to the minus 5. What did we say it was? We said 50 microstrain. We're right on the money. Right on the money, okay? Now, we also can calculate out what the strain should be in. And notice that these values, all right, so this value is kind of on the right order of magnitude, right? And this value, even though it's like a max, it's also kind of on the right order of magnitude. But again, I wouldn't trust them. Look, that's like 40% off or 60% off. Okay. So now let's look at the strain in the y. Now look, is there a y stress? No, we said 0, right? But there is an x sigma x, right? And there's a Poisson ratio, so there's going to be a non-negligible strain in the y direction. Okay, and that epsilon z is going to equal epsilon y. So if we look at the stresses in the normal, if we look at the normal strains in the y and the z directions, we should expect to see something. So let's see what we see. Okay, and so let's look at epsilon 2. Look at that, minus 1.5 e to the minus 5, minus 15 microstrain. Okay, look at this, minus 15 microstrain. Again, other stuff is happening near the in other parts, but at least in this region that's far away from all the craziness at the boundaries, we're getting a very nice result that matches what we had. Okay, any questions on this? Yes.
The elements that we created on this, are they throughout the volume or just on the surface?
They are throughout the volume, but we're only looking at stuff on the surface. Yes. Are there ways to interrogate the insides? Yes. Is it easy to do in pre-Pomax? No. Okay. But yes, often what you'll do is you'll take a cut and you'll be looking inside. For these problems, for most of the problems that we'll be doing in class, we're just looking at what's happening on the outside. Okay. Or what's happening on the outside is enough, right, for us to understand. But absolutely, a good package and a good user will be able to get into the insides of this. Good questions. All right. So this is kind of fun. What do you have for your assignment? You just get to put in a geometry and run some numbers, and you get to put up a screenshot of this. Okay. What have we learned so far in Canvas? The numbers change every time. I'm sorry. Okay. I don't like it either. Okay. It's just that's how it works. Okay. So this assignment is notoriously bad for people not putting in the right number for the normal stress or the normal strains, getting that part wrong, but having done the simulation already, and then they have to redo the simulation. Okay? There's not a really good way to navigate this. So what I would say is, before before you kind of hit submit, all right, make sure that your calculation by hand matches the calculation you have here, okay? All right, because the screen's not going to change. It's not, or you can even close Canvas, right? That problem that's for you at that given moment is fine, okay? But the calculation, that the number that they want, that I'm asking you for, is from the hand calcs. The screenshot needs to show the same result as the hand calcs. Does that make sense? Okay. So just save yourself a little. Don't be trigger happy, right? Go ahead and take some time. Make sure the calculations are right. Follow exactly what we did here, and you should be fine. Okay. And there's also a tutorial that Siobhan put up now, I guess, a year ago or so. We'll leave this open because there's something else I hope that we have time to do in a little bit. You can now put, after the semester, on your little resume or your big resume, all right? I have some experience doing finite element analysis after you do the exercises in this class, all right? Because it's not that complicated to do, all right, in this respect. To understand the theory, to really get down and make sure that you've got complex, that you're replicating complex phenomenon. That's hard. That's really hard. Okay, and that's ongoing. People are doing their PhDs on this type of stuff, especially in the area of fluid structure interactions. If you're a mechanical engineer, like turbulence and fluids, it's really rough. It's really rough. Okay, so this will be one of your questions. So again, it's asking what's the axial strain, okay? So make sure you get an axial strain that matches what you have in your simulation before you submit these things, right? Because you're going to be frustrated if this says it's wrong. And you'll be frustrated if your image doesn't match it too. And then there's another question. Question 2 is, what is the strain in the direction of the height of the bar? Okay, what does height of the bar mean? In this case, that meant in the z direction. Okay, not the length. That's epsilon 1, right? We're asking you for what is epsilon z. Okay, and notice it says in microstrain. So make sure you multiply, by 10 to the 6, right? These are just some of the hiccups now. At this point in the class, these hiccups happen. It's just now it's a pain because you had to go back and redo your finite element again, right? And it's also a pain because this problem will give you different numbers than this problem. So you have to do 2 finite element models. Right? All right, let's go to the thermal strain and stress. When you hear thermal expansion, what do you think about? Yes, Michael? Huh? Heating causing expansion. Yeah, okay, good. What else? I can't hear that. What? Say that again? Huh? Oh, contraction when it's cold. Is that what I heard? Yeah, okay, yeah. That's great. Okay. When do you experience that thermal expansion and contraction in your daily life? Bridges? Okay, so the bridges that you're going over, they're going to be contracting, right? Like if you ever, even if you're on a bike or you're walking over a bridge and you see some of these like somewhat flexible joints, okay, linking them, you're like, hey, why is there a larger gap today than it's like, oh, this is weird, it's moving. So yeah, that happens, yes? Sure, yeah, so you have, I hadn't thought of that. Yeah, your food, of course, can expand or contract. It's interesting, though, what happens with ice, though?
That's the one.
It goes back, it crystallizes and it actually expands, which is against these kind of linear relationships we're talking about. Yeah. What else? Anything? Yeah?
Anything that flies fast.
Sure, you're going to have some heating up and cooling down. And so thermal contraction can come in there. We live in an old house, all right, and even a new house. But the house makes all kinds of noise in the winters, right? Because you've got the heaters, you got these things that are expanding. You've got all kinds of freaking throughout the house at different times of the night and in the morning, right? Why is that? It's because things are expanding a little bit or contracting a little bit as the temperature fluctuates. Knowing what you know now, can thermal expansion and thermal contraction, can it affect the distribution of stresses in a structure? Yes, you know that, right? That's rhetorical. Do we have to worry about them? Are they significant ever? Well, today you'll know that they are significant. And one way to think about it is do the inverse problem. What were we just talking about here? We're talking about 15 microstrain. We're talking about 50 microstrain. Right? And that was associated with 1,000 newtons. Imagine if you have a constrained bar and the thermal expansion causes it to, if it were not constrained, right? If it were not constrained, it could go 50 microns. But then I've got to push it back 50 microstrain. Or, I had to use a force that induced a negative 50 microstrain to get it back to its original shape. That's 1,000 newtons of force, right? So these effects from thermal expansion and thermal contraction can have significant impacts on the distribution of forces, internal forces, and distribution of stresses in an object. Okay. So you've probably in chemistry, right? You've done this, or maybe in physics. When did they teach you thermal expansion now in high school? They teach it, right? Maybe? Somewhere? No? Huh? Second year of what? High school. In what? In physics. Okay. All right, so you've encountered it before in physics. So what we're saying here is, and this is probably the equation you saw before, that a change in length is going to be equal to some coefficient, okay, this alpha, times delta T times L. Okay, so change in temperature, the thermal coefficient of thermal expansion, that's the alpha L, alpha sub L, and times its original length. Okay, that's the base equation. But you know something now that you didn't know before. You know what thermal strain, or you know what linear strain is, right? So look, all we do is we move this L under here, right? And this quantity then becomes axial strain, and we can define a thermal strain just in terms of the alpha sub L times delta T. If you have a bar suspended in space, or even if you have a bar kind of constrained on one side or somehow held, and I apply temperature to it, and it expands, and it's free on this side, what is the stress in this object? Someone else who hasn't. This is one of those math questions. It's 0 or 1 is a good guess. Okay. What is the stress? It's 0, right? Okay. You can have. This is an interesting situation. With thermal expansion, you can have strain when you heat something up, but there's 0 stress in it. Okay? And you think we walk around all the time and we have, things are expanding and contracting, and if they're not constrained between objects, there's not going to be any stress in them. So this is just saying that the internal force with a free end bar is going to be 0, and the internal stress with a free end bar under thermal expansion is also going to be a 0. Now, there is also something called a volumetric coefficient of thermal expansion. All right, I don't think I've ever said this is the volumetric. Maybe I have, but I'm not going to. I commit to not give you a volumetric coefficient of thermal expansion. But if I were to, it's not that complicated. All right. Remember, we introduced dilatation or the volumetric strain, right? And it was epsilon x plus epsilon y plus epsilon z, which is equal to 3 times. So look, if you've got volumetric strain, okay, volumetric strain, all right, you see there's a 3 times this mess. So what we have is that the volumetric strain is equal to 3 times the linear, or sorry, the volumetric coefficient of thermal expansion is equal to 3 times the linear coefficient of thermal expansion. And so this table, it's not that exciting because, well, a lot of these values are just a factor of 3 okay, between each other. What are some things that you noticed here? Just look at the data. You don't have to be a neural network, but use your brain. What do you notice here about some of these materials and their coefficients of thermal expansion? What are some things? Yes? Right. Well, we established that. Okay, good. So factor of 3 larger. Okay. All right. Good. What else? Yes.
The metals typically have a lower coefficient compared to the liquids.
Yes. 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 Look, those polymers, they're rocking it. Okay, or the liquids are rocking it. Right. These petroleum-based, even water. All of these have a larger, right, thermal coefficient of expansion than the metals. What does this mean, though, in terms of importance? Well, if you have an application where you want, let's say you're designing an atomic force microscope, okay, or you're doing something at the nanoscale. If dimensional stability is important to you, polymers are a pain. Okay, it doesn't mean that's a game breaker, but it does mean that it's going to be trickier if you're heating and cooling than some of the metals. Okay, and some of the ceramics are even better. Okay, in terms of having low coefficients of thermal expansion. Okay. So that's another thing. Yes. Interesting question. Less heat. Less. So metals require more temperature, right? We didn't go to heat. We didn't talk about heat. Why is heat a loaded question here for this class? Well, right? If you've done some thermodynamics, now you know what a heat capacity is, and you know what specific heat capacity is, right? And what is that? That is how much the temperature changes, right, based on change in energy that we're putting into the system, right? So we haven't said anything about heat here. We're just talking about temperature. But a lot of these metals have a higher heat capacity than some of the polymers. Okay, and water has a really high heat capacity too. Okay, so yes, if you're looking at how long do I have to have my flame, or how long do I have to put this in the oven to get it up to the temperature to then cause this expansion? It's going to be dependent on its heat capacity as well, but we're not talking about that. Okay, good. Yes.
Do harder materials tend to have a lower
That's a good question. I mean, I'd say that's probably, let's call it this. If you had to make a plot on one axis of coefficient of thermal expansion and elastic modulus, let's not say hardness, right? But elastic modulus. And elastic modulus and hardness are often correlated with each other, but we know that hardness is kind of with the strength, and so we can tune strength. But you could kind of say, sure, probably the higher the elastic modulus, the lower the coefficient of thermal expansion might be. Maybe. Okay. This gets to another point that I want to bring up. If you have a system where you have a polymer on one side and you have a metal connected to it, and you constrain them between two walls or in a system, or even like this table, right? It has polymers against as wood, I guess, and there's some polymer here, but you see there it's multi-material, right? There are going to be these tug of wars or push of wars, okay, between these materials. And the metals, because they have such a high elastic modulus, even though their coefficient of thermal expansion is small, they can make life squishy and hard for the polymers around them. Okay. All right. And then there are other effects of temperature on these materials. Besides just their change in shape, you have, change in strength. They can also become brittle, right? And we talked about the O-rings and the Challenger a couple days ago, right? We did? That was here, right? I forget where I've been and what I've said. Okay, but in that case, the O-rings on the solid rocket boosters of the Challenger of the space shuttle, right? They got to a low temperature, and not only they would have contracted a little bit, but there they became stiffer as they got colder. And so that caused problems in terms of being able to form a seal because it didn't squish as nicely into protecting the gap as much as its a softer version would have at a higher temperature. Okay, so here's an example. We have an unconstrained bar, length 1 meter, and a cross-sectional area of 1 centimeter squared with elastic modulus of 70 gigapascals. If we heat the bar uniformly from 20 degrees Celsius to 212 degrees Celsius, what is the change in length of the bar? So we might break this problem into the 3 pillars: equilibrium, geometry, and constitutive equations. So for equilibrium, this is a free floating bar, unconstrained bar. So equilibrium is not so interesting here, okay? So it's just 0, right? 0 force, 0 stress. Geometry can change, right? And if it's free floating, you could argue that one side goes delta over 2, the other side goes delta, whatever, right? But we know that we're going to have some expansion. What is the prime constitutive equation that we want to use? Well, not that one, but this one would be, the other one's important too, right? Relating the volumetric coefficient of thermal expansion to the linear coefficient of thermal expansion. And we know, I guess you could have written out that the delta is equal delta T times the coefficient of thermal expansion times the length, right? But this is our more technical version that we know of because we've been working with strain a little bit, okay? And the change in temperature is important. So, you could write it in terms of Celsius, you can write it in terms of K. Either way is fine. This thermal coefficient of expansion, the volumetric one, right, was given in, units of strain per K, okay? But it could be equally written as units per strain per C, degrees C. I guess I was lazy, or not lazy, I was probably in a rush when I wrote this, but I didn't do like the little degree symbol. That's the nice thing about using K, there's no degree symbol. All right, so we have now ability to calculate the delta, and we can put that into some code if we like, but it's really just, okay, take this number, divide by 3, times the change in temperature, times L naught, and that's the change in length. Not insignificant, really. 4 millimeters, I'd be able to see that. But putting in a meter-long bar into my my pot at home, I'm not gonna. That's probably hard to get. Because I gotta get a lot of temperature, right? That's over 212 degrees Celsius, right? I don't know why I picked 212 degrees Celsius because 212 degrees Fahrenheit is 100 degrees Celsius, and that's boiling. But anyway, 212 degrees Celsius is very hot. Questions? Yes? That's what I'm saying is that they're interchangeable here, right? Because we're interested in deltas for the temperatures, changes in temperature. All right, you got to start from somewhere and go to somewhere else. Okay. How we are running, oh, I'm so behind. Okay. This is a hard problem. Okay. It may not look like a hard problem, but it is. And you should be comfortable with these types of problems, and the assignment will help you get comfortable with them. They're painful. All right. There are two ways to do this. I'm going to show you the first way, which uses that idea of superposition, where you expand something and then we apply a force to constrain it. And I thought that would be the easier way to approach this problem. No. I think the geometric compatibility, the second thing I'm going to show you, is an easier approach. At least fewer lines of writing. Okay, but this is kind of a classic problem, and it helps us understand this push of war, this tug of war between materials that are constrained between two walls. So we have, a bar with an elastic modulus, some length, and some cross-sectional area. And what we're saying here is that the cross-sectional areas, those are going to be the same. Okay? They don't have to be, but they are. And but everything else is different. Right? We have a alpha 1 and alpha 2. We have elastic modulus 1, elastic modulus 2. We have a length 1 and a length 2. Right? And now the question is, what are the axial strains in both sections? So let's try to use our three pillars again. Equilibrium, geometric compatibility or geometry, and our constitutive equations. For equilibrium, okay, this is something that's interesting and maybe a little counterintuitive. Right? I can say, oh, I have an F1 right on this side, and I have an F2 on this side, and they're going to be pushing in, right? This thing is expanding, assuming that I guess I didn't say that. But let's say that assuming the change in temperature is positive. Okay? We got expansion, and so there are going to be forces from the outside pushing in. As it says there, those forces, they are the same. And you're like, wait, no. Bars between walls don't have the same forces on both sides. That's what I've been taught. What we've been talking about. This does not have an external force applied in the middle. Okay? So if I look at this from an equilibrium, and I'm doing external equilibrium here, right? There's no internal force, just temperature being applied to this system. And what do we get? We get this force has to be equal to that force. Which means that the force in this bar and the force in this bar are going to be the same. And this is kind of like, oh yeah, I remember you said we have springs in series, right? This is kind of like a system that's behaving like two springs in series now. Okay, so we're going to use the method of superposition with the forces. What does that mean? That means first think about it unconstrained. So you're going to have a delta 1 associated with the deformation of the left one, and a delta 2 associated with the deformation of the right one, and the total deformation is going to be the summation of those two. Let's think about some constitutive equations. So we like to think of things as effective spring constants, right? And we can think of an effective spring constant for this entire system, right? What do we say here? These are like two springs. When it's unconstrained, two springs acting in series. And that's what we have with the K effective. We also know that if we want to figure out what the local K's are, and if I know what the elastic modulus is, and the area and the length of these regions, I can figure out what a local K is, right? So I can figure out what my K1 is over here. I can figure out what my K2 is over here. We also know that this delta can be given by alpha delta TL. We also know that sigma is equal to E times epsilon for cases where there's a load. Okay, if it's a thermal, so be careful here. This is a force, or this is a stress. This is a force-based equation. Obviously, we can have some epsilon thermal if it's unconstrained that has no stress. We've already discussed that. Okay. So here are some thermal expansions. We can write it as a displacement for this bar. We can write it as a strain, which would be uniform in this region on the left. We can write it for the second bar or second region as well. Okay? Now, what is the unconstrained delta on this end? Well, it's just going to be the summation of these two equations right here. Thermally. Unconstrained, meaning I've removed one of the walls. So what does this mean? This means that the force that I apply to the system has to overcome this amount of displacement. Okay? So we're going to apply, F1 or F2, they're the same, and we're going to constrain it to constrain this displacement. Okay, and so what is that force going to be equal to? Well, I figured out what my K effective was over here, and I know my K effective times my delta is equal to force. So the force that has to be applied by these walls has to be equal to the displacement from a thermal unconstrained, the unconstrained thermal expansion times the K effective, right? Does that make sense? So we have F1 and F2 are equal to each other, and this is how you calculate them. Right. So now, okay, I can figure out what the delta due to force is in each of these, right? Because I've got this force, this could be F1 or F2, whatever it is, F1, or it's equal to F, right? If I divide by the K1 for this one, then I know what the delta is, okay, due to this force. This is due to force, though, okay? And that's in compression. There's still some displacement due to thermal expansion. And there's a tug of war, right? There's a tug of war. Like, is this mid-region, is it going to the right or is it going to the left? Remember, everything is being elevated to the same temperature. Okay. So if I have a very, very stiff material on this side with a very high coefficient of thermal expansion in comparison to the right side, the left side is going to win. It's going to push the other one, right? Over. Okay? And here's another interesting thing. So the epsilon, the strain, because it's axial strain, the strain in the left region is going to be equal to the thermal strain plus the force space strain. And the epsilon 2 is going to be equal to the thermal strain plus the force space strain. Okay? And this is maybe a little bit counterintuitive. It's dangerous to add strains to each other. Okay? I understand it's more intuitive to add displacements to each other and add forces to each other. And even maybe add stresses to each other. Okay? But these strains and stresses, if we add them to each other, they better be acting in the same direction on the same face, right? Do not. It's like adding fx plus fy. That's like, don't do that, right? Okay, so then we go on. Oops, there's the answer. Oops, I guess I didn't cover it. All right, so remember this. This is just the delta overall. This is the K effective, and this is the force, right? And now we're saying that we know that K1 is equal to E1A over L1, and K2 is equal to E2H over L2. We can figure out what the mechanical stress is, right? And sometimes people will say mechanical, right? It's not thermal, so it's mechanical. Okay, but this is all mechanics. So that may not be the best way to put things, all right? And we can figure out what the mechanical strain is by doing F over EA. The thermal expansion, we've already talked about that a little bit, all right? And we said that we could, and so this is going to be the mechanical strain in both of these cases. And then we put all this together, all right? the mechanical strain and the thermal strain, okay, which we calculated out here, okay. We've calculated out our thermal strains here, okay. We put them all together. That's just the alpha. See, it's not that complicated. The thermal strain actually is pretty easy. Epsilon 1 thermal is just alpha 1 delta T. But this mechanical strain was a pain all right? And we had to calculate it out. And same thing here. This thermal strain is the complicated one, all right? So, that is one way. That's the answer, okay? That's kind of nasty, but that's the answer. How would you do this just using geometric compatibility? Well, I'll try to quickly go through this in 2 minutes. We break into 3 categories, like this, and we say from geometric compatibility, the deformation, so sometimes we say delta B relative to A, right? So this is the deformation in this region, and delta C relative to B, right? The deformation in this region, that has to be equal to the deformation from C to A. But the walls are not moving, so that's equal to 0. So now we know the deformation of this left one plus the deformation of this one is equal to 0. And we know what the K's are. Okay? We have constitutive relationships again that we can use. And we can calculate the total strains as just being the delta BA over L1, right? And the delta CB over L2. These are just definitions of strains. Now, what is delta BA? This is interesting. This is going to be what it would have been in its unconstrained state minus the F over K1. All right? So I didn't like separate them. I mean, it's kind of like doing the same thing, but they've been compressed or they've been combined here in equilibrium. And it's actually in geometric compatibility, sorry. And that's the same thing for delta C relative to B. Then I add these together, and they have to be equal to 0. And now I have a force, right? You see that's the same force. I know everything else. I know K1, I know K2, I know alpha 1, I know delta T. What I do not know is the force. So I can solve for the force, then I can put it back in here, and I can put that over this, and that gives us the strains. Okay. Any questions on that? So that is arguably a shorter way to do the problem. Either one would be fine. It's just very important that we keep track of how the strains are adding to each other, what's mechanical, and what's thermal. That concludes our technical portion for today. So there are 3 questions. They're due on Thursday. This is the last bit of information that you got to cram in your heads before Tuesday when we have the exam. Let's go ahead and we'll do the, let me post the slide, okay, for everyone's attendance. Are there any questions, comments, concerns while we're doing this? Oops, yeah, there we go. Okay, go ahead. So Thursday will be fun, and it will be important for the next exam, but not for Tuesday.